So yeah, in this class we'll be seeing. See, this will be a long class. Okay, there will be almost like I think 45 slides. So we'll be taking more than like at least 2 hours. So we'll be discussing about the coordination component importance. We'll be seeing about the classification of the salts. We'll be seeing the general formula as well as we'll see all these terms. What is the central metal atom, ligand, coordination sphere, ionization sphere, and coordination bar. Okay. So just let me know if you don't understand anything, please ask. Okay. Okay. So salt. So what is salt? It is a ionic compound that contains both the cation and the anion, right? So a ionic compound. It's not a covalent bond. Okay, it's not a covalent compound. It's a ionic compound. So ionic compounds are formed by donating. Okay, that's a complete transfer of electrons. So here the salt is formed by complete transfer of electron between the cation and the anion. So the cation will donate the electrons and the anions will receive the electrons. So it contains a cation and an anion. The cation, we call it as the basic radical, and anion, which is called as the acid radical. We'll be seeing what is that basic radical and acid radical. Okay, so just know what is salt is just a ionic compound where it contains both the cation and anion. Okay, there are different types of salts are there: simple salt, double salt, and a complex salt. So what is simple salt? So simple salt is formed by neutralization of acid and base. For suppose you take an example, NaOH. Okay, when it reacts with a HCl. So here the NaOH acts like a base, and HCl is a strong acid. It's a strong base and a strong acid. When they react, there will be neutralization will happen. That is NaCl plus water. So what happened in this? It is a neutralization reaction. Okay, where the hydroxide ion from the base, it will combine with the hydrogen present in the acid. Okay, so that's how OH will join with the H. Meanwhile, whatever the sodium is there, that sodium will join with the chlorine ions. So they two combine and it will form NaCl. OH and H will combine and form the water. Okay. So remember, the sodium hydroxide when reacts with hydrochloric acid, both are strong base and strong acid, it will give the sodium chloride, which is a simple salt, and the water. Understood? So the basic funda for the simple salt is producing a salt and water. Understood? So whenever an acid and base reacts, it will produce a salt and water. So this is a very small example, simple salt. What is the double salt? It is formed by the combination of two or more stable compounds in the stoichiometric ratio. Remember this. Okay. So what happened here? There will be two salts. So the double salt, it will be created by combining two or more different stable compounds. Remember this. So two or more stable compounds. Okay. And they should combine in a very specific and precise, in a proper proportions. It is not arbitrary. Like I'll be taking one compound like two and the other compound like three and I'll join, it will become a double salt. No, there will be proportional stoichiometric ratios are there. Only in those specific proportions, the salts will combine. Is that clear? So remember what is meaning of stoichiometric ratios is they will combine in a very specific proportions. Okay, so there will be stoichiometric ratios. Okay, so these proportions cannot be any random. Okay, it should be very there will be particular ratios are there. We'll be calculating based on different things, different parameters. Is that clear? Guys, please respond. Is that clear? What is double
Yes.
salt?
Yes.
Okay. One more thing you need to notice here. That's a very, very, very important thing. So write down this. The unique property for the double salts is they show a very characteristic behavior. That means how do you identify the double salt, multiple salts, and the simple salt? Okay. So there is a characteristic one. That is, there's a characteristic property, or you can say the behavior. That means they can completely dissociate into simple ions. Remember this. Okay. So this complete dissociation is the defining feature. You can differentiate these double salts from the complex salt formations. Okay. So if I have given you the double salt and the complex salt, if you see the double salt, they will be simply dissociate into simple ions. So whatever the ions that are present in that, they can be differentiated, but that will not happen in the complex salts. That we'll see when we discuss about the complex salts. So generally the complex salts will retain their original structure even if you put it into the water, but here it's not like that. Okay, so just remember, it will dissociate into simple ions when you dissolve in the water. So that's a unique property for the double salts, or you can say that is the characteristic behavior for the double salts. Is that clear?
Yes.
Let's see an example for the double salt. So here the potassium chloride, KCl, okay, it reacts with the magnesium chloride and water. It will be forming a complex structure that is a double salt, which is KCl, MgCl2, 6s2. So all these are combined together. Okay, we call it as carnallite. Remember this, which is a double salt. You can see here KCl is a salt, MgCl is a salt. So two salts were present. So it's a classic example for double salt. So remember, if you are asked what is the characteristic for double salt, so first one, it will form a very stable compound. Second one, it will those two salts will combine in a stoichiometric ratios. It will not combine in a random way. There will be specific stoichiometric ratios are there. They will combine only in that particular way. Okay. And when you dissolve this in the water, they will completely dissociate into ions. Okay. They will produce the simple ions like K plus, Cl minus, Mg plus 2. Okay. Cl2 minus 1. Sorry, Cl minus 1. So like that, they will be differentiated into very simple ions when you put it into the water. So remember this, produce simple ions by dissolving in the water. So upon dissolving in water, remember this, and they combine in specific stoichiometric ratio. Is that clear? Understood? So just remember KCl, MgCl2, 6s2o. Okay. So what happens when you dissolve in water? So the K, it will produce the K plus. Cl will produce the Cl minus. Mg, it will produce the Mg plus 2. And Cl2 will produce the Cl minus. Okay, so you will be seeing the solution. If you see, it will be precipitated with Kg plus Mg plus 2 and Cl minus ions. Remember this. Okay, so they were dissolved or dissociated into very simple ions. That's a characteristic property for the double salt. Okay, so that's about the simple salt and complex double salt. But the agenda today in the coordination compounds is studying about these complex salts. Okay, so what is a complex salt? It is formed by the combination of two or more stable compounds, and this also happens in a stoichiometric ratio. But how do you differentiate this with a double salt? Here, one is it could be two or it could be more than two. That is one thing. Okay. Whereas in the double salt, it is only two, not more than two. Second thing is in the double salts, when you put it into the water, they can simply dissolve into ions. But when you put the complex salts into the water, they doesn't dissolve. Doesn't dissolve into simple ions when dissolved in water. This is the unique, or you can say this is the defining character of a complex salt. So it will not dissolve, whereas the double salts, it will dissolve into simple ions. So remember this. This is very, very important. So how do you differentiate the complex salt and the double salt is double salts will not double salts will dissolve in water. Complex salts will not dissolve in water. Is that clear? So this is the very important characteristic for the complex salts. Okay, dissolution behavior. That's a if you see in the double salts, they will be dissociate into simple ions, whereas here it will not dissociate into simple ions. Is that clear? Any doubts?
No, sir.
Okay,
No, sir.
perfect. So here, let's see as an example. You can take here KCN plus FeS4. It will give K4 FeCN6 plus K2SO4. Okay. So see here KCN. What is KCN? It's a potassium cyanide. So this potassium cyanide, when it reacts with the FeSO4, you can say this is a iron sulfate. Okay, or you can say iron 2 sulfate. Iron 2 sulfate. When it reacts, it will produce the potassium ferrocyanide. I'm not giving the IUPAC kind of naming that we'll discuss in later classes. So right now I'm just giving the common name potassium ferrocyanide and K2SO4, which is a potassium sulfate. So yeah. So what happens here? You take this one, FeCN6. Okay. So you take this FeCN6. It will break down into -4. Okay. How do you tell that? We know potassium, it's a +1. So here FeCN6, it will break down into -1. So like that, 4 are there. So -4. Okay. So that one thing. And second thing, if you dissolve this, if you put this in the water, it will not dissolve into Fe plus 2 or Cn minus. Remember this. Okay, so this will not dissolve. It will not dissolve. Doesn't dissociate. Remember this. Okay, so when you put it into the water, they will not dissociate into very simple ions. They will, it will retain this structure. Okay, it will not break down into Fe plus 2 or Cn minus. It will retain its structure. Is that clear? And remember, we'll be talking, but just now, whatever this Fe is there, it will be the central metal ion. Okay. And whatever this Cn is there, it's a coordinating ligand. So first there will be metal and there will be ligands are present according to the alphabetical order. Okay. Remember this. So this FeCN6, we call it as the complex ion. Okay. That all these terms we'll be seeing just now, you notice it. So is that clear? What is complex salt? Any doubts?
No, sir.
Okay. Take one more example. You can take Fe. Once again. Yeah. So FeCN2 plus 4KCN. It will be giving FeCN2 4KCN. Remember this. Okay. So actually this FeCN2 4KCN, it's also called as the potassium ferrocyanide. This is another form. Okay. This one you can also write in this form. If you don't want to put into the brackets and all, you can try it this way. Okay. So this is also a potassium ferrocyanide. Okay. Let's see the complex salts. Remember? Yeah. Here also it will not dissociate into Fe plus 2 or Cn minus. So this will not happen. Remember this. Okay. So it will not dissolve in the water. It will maintain. Okay. Distinct entity. Let me show this way. Yeah. So K for FeCN6. So here in this, whatever that you put into the square brackets, they are called as the complex ions. Remember this. So this is called the complex ions. So what are complex ions? Those that put in the square bracket. Okay. And remember this entire structure, it will be a distinct entity. Okay. That way I'll tell you what does that mean. Okay. That means whenever it will break, this one will break into the K plus structure. And whatever this entire thing is there, it will be break down into another structure that is FeCN6 4 minus. Okay. If you see here, this FeCN6, it will not further break into the simple ions. Okay. Not break into simple ions. So that's it. Here, from this, you can say the FeCN6, it is retaining its structure. When it is retaining its structure, we call it as the complex salts. So let's see what is this complex salts. So these complex salts are nothing but they are the coordination compounds. We'll be studying in detail about these coordination compounds. Okay. So coordination compounds. The addition compounds that retain their identity, that means they do not lose their identity. When you dissolve in the water, they are called as coordination compound. So what does that mean? When you give K for FeCN6, okay, this one, it will not break into KCN plus FeCN2. Okay, so this will not happen. This will not happen. So it will retain its structure. Okay, it will not give away into the, it will not further break down into KCN or FeCN2. So those compounds are said to be coordination compounds. It can dissociate into K plus and FeCN6 minus, but it will not form into the other compounds like KCN or FeCN2. So that is what the coordination compound means. If the definition asks, it is the addition compounds that retain their identity, which will not do not lose their identity in any solutions. You put it into the water or any solutions. That's called as coordination compounds. Okay, so that's how you can be differentiated with the simple ionic compounds and the coordination compounds. In the coordination compounds, they cannot differentiate, but the simple compounds or simple ionic compounds, they can differentiate into the other compounds. Okay, but here they will maintain or they will remain intact. See, I'm stressing too much because to understand, if you are given with any example, you should be able to identify between the coordination compound and the double salts. Okay, so remember this. So see here, this one remain intact. Okay, so that's how it will preserve it's a chemical structure. It will not dissolve into some other structures. Okay, whereas you take any other ionic compounds, they generally dissociate into different compounds. But here it doesn't happen. Okay, so that's why they kept into some different concept. So see here, the metal atoms are bound to a number of anions, cations, or neutral molecules by sharing the electron. First, suppose you take this. So K4 FeCN6. Okay. So here, whatever the Fe is there, it acts like a center metal atom. Central metal atom. And whatever the CN, there are six cyanides are there. These groups will act like a ligands that will be surrounding around the central atom. See, you will be need to calculate the coordination compound complex number, all these. For that, you should know these terms. Okay. And remember, whatever the four potassium ions are there, they will be helpful for balancing the charge. So this will balance the charge. Okay. So this is said to be a ligand. Okay. So there are six cyanide groups are there. These all will be surrounding this central metal atom. So if you take Fe, it will be surrounded by this central atom. Okay. So that's how it will be when you see in the structure. Okay. And how does this coordination compound will be formed? Where this metal atom, it will be sharing the electrons, okay, with the other structures. So that's how it will be formed. So that's what he says. The metal atom, it bound with any anion or cation or even the neutral molecule by sharing the electrons. So that's how a metal atom is bound to the ligand, and this bond is a very strong bond. That's why they cannot dissociate into ions. They will be living like a together. So let's see how do we do the general formula for coordination compounds. See, if you want to write a general formula, you should follow with these things. Write down these formula, I mean, these points. Like how you have IUPAC naming, there will be certain rules and regulations are there. So that you should know. First, let me take an example. So FeCN3. Let me write here. Fe. Okay, 4 minus. So this is the general formula, remember. Remember this. This is very, very important. Okay, so let's say few things. So first, whenever you are writing the coordination compound, okay, so general formula for coordination compound. The first thing you should know is you put it into the square bracket. Okay, whenever you write a coordinating compound, it should be in square brackets. This is a important thing. So next one, after putting in the square brackets, the first thing that you need to write is a metal atom. Here, iron is the metal atom. Okay, so M means the metal atom. So remember this. So metal atom is written first. That's the second important thing. After that, you will be writing all the ligands. Here, cyanide is a ligand, NO2 is a ligand. So you will be writing all the ligands. And how do you write? Based on the alphabetical order. For suppose this starts with C, so it comes first, and then N comes later. So you should write the ligands in alphabetical order. So write ligands in alphabetical order. Okay. Next thing. Whatever the charge is there on this complex species, you should be writing at the top right corner. Okay. So this is the right and top corner. So remember this. Charges are written on complex species is written on top right corner. So charges on complex species is written on top right corner. Okay. So you may ask question, sir, what is this ligand? Okay. What is this ligand? So ligand, remember this. So what is this ligand? Okay. It is just an atom. It is an atom, or you can say a group of atoms or you can say the molecules, or it could be even the ions. Okay, so which donate an electron pair to central metal atom. Understood? So what is ligand? So it's an atom or group of atoms or molecules or ions which donate an electron pair to the central metal atom. Is that clear? Any doubts?
No,
Okay. So let me show you another example. AgNS3 twice plus Cl minus. Okay. So you can see here, this is Ag is the metal, and whatever the NS3 is there, it's a ligand. And on the top, A plus is there, and on the right, A minus is there. Okay, which is a X minus. So the general formula is like this: M L N. So here N means number of ligands are there. It could be here 2, A plus X A minus. Okay. So remember in this thing, whatever it's there, this one. So this we call it as the coordination entity. We'll be talking what is coordination entity, but just now remember this entire thing is coordination entity. It will exclude this. Whatever the chlorine is there, it will not come. Only this part will come under coordination entity. Understood? So what is this coordination entity? See, what is this coordination entity is, it constitute, if you see here, what is there? It is a metal is there and their ligand is there. Okay. So you can say a coordination entity means it constitutes a central metal atom, and there is a ions are there bonded to fixed number of ions or molecules. For suppose you see here Ag, it bond with fixed number of ligands here. Okay, I told you what is ligand. Ligand is nothing but atom or group of atom or molecules or ions which will donate the electron pair. So here the ammonium acts like a ligand, and this metal atom is bound to the this number of ions in a fixed manner. Okay, that means Ag will bind to ammonia only twice. It will not be like Ag plus NH3 1 or Ag NH3 3. You can't write like that. There will be fixed proportion is there. You can say the stoichiometric proportion. Okay. So see here, what is coordination entity? It constitutes a central metal atom, or you can say, or ion bonded to fixed number of ions or molecules. So you can take many examples like FeCN6 4 minus. or you can take Ag NS3 plus. We'll be seeing how they got this -4, how they got plus. Okay, so we need to calculate the charges also. So remember this. Okay, you can also take CO NS3 6 plus 3 3Cl minus, or you can say Cl3 minus. Okay, so tell me what is the central atom here? Bonnie, you tell me what is the central atom here?
So it is NH3 whole 6.
Banu, what are you listening? Central atom. What is central atom? I told you now here. So metal atom is written first and that will be the central atom, right? I told you many times here. See, what is a central metal atom? And whatever that first thing that we write, it's a central metal atom. And all the things, the ligands comes later. So tell me, what is the central metal atom here?
So CO.
Yeah. Okay. So this is a central metal atom, which is nothing but the cobalt. Mandara, you tell me what is the ligand here and how many ligands are there?
NH3, sir.
Hmm. How many ligands are there? Mandara, how many ligands are there?
2, sir.
Hmm?
2.
6 ligands are there. See, NS3 6 number are there. So 6 ligands. So 6 NS3 ligands are there. Okay. So which are coordinated to the central metal atom. So 6 ammonium ligands coordinated to central metal atom. Or you can say central metal. Shrikar, you tell me what is the overall charge, overall complex charge?
Yes, sir.
How many overall charge is there? What is the overall charge here? Overall charge of the complex.
+3.
Yeah. So +3. This is the overall charge. And it is balanced by the 3 Cl minuses. So here the Cl minus will act like a counter ions to balance this +3 charge, which is present on this coordination compound. Okay. So +3. Understood. So remember, do you remember the formula for writing this? So M L N A plus X A minus. Right. So let's see each of them. So first one, is the M. That's nothing but the central atom. So remember what is M? It's a central atom. So generally these central atoms are metals. So central atom is generally, it is a metal atom or ion. Remember this. Okay. And remember one more thing, this central atom is always a Lewis acid. What is Lewis acid? Tell me, what is Lewis acid? Anyone?
So,
So, yeah.
so just a triamine group, right?
Hmm?
Is the amine group considered as Lewis acid?
No. Just simply say what is Lewis acid. For suppose you will say what is cation means it's a positive charge ion which got by losing electrons. Anion means you say it is a negative charge ion which got by gaining of electrons. So like that, what is Lewis acid? Okay, no problem. So just remember Lewis acid means it's a lone pair acceptor. You know what are lone pairs, right? Yes or no? Lone pair and bond pair, you know, right? So every atom, for suppose you take the oxygen is having two lone pairs and one bond pair. So this will be involved in the bonding, and these two will not involve in the bonding. So those which will not involve in the bonding, usually they are called as the lone pairs. And this actually involves in the bond pairing with someone else. Understood? So here, if the oxygen donates this pair, we call it as, okay. So it donates. Actually, that will be Lewis base, and this is called as Lewis acid. So remember what is Lewis acid?
So,
It's a lone pair acceptor. Okay. So one more thing you need to remember here. So whatever the central atom is there, in a coordination, entity, how do you define this central atom? The atom or ion to which fixed number of ions or groups are bonded, or you can say are bound in defined geometrical arrangement. We'll see what is the geometrical arrangement around it. So that's known as the central atom. Or you can say ion. Okay. So see here, what is central atom? Central atom means if you take a coordination entity. Okay. So the atom or ion to which fixed number of ions or groups are bound. Okay. Here the fixed number of ions or groups means they are ligands and they are bound in a definite geometrical arrangements. First, suppose let's take an example. So here you have a cobalt. You have a cobalt NS3 6 plus 3. You can take a 3Cl minus. So see here, in this is the coordination entity. Okay, we'll see what is coordination entity in detail, but this is the coordination entity. Yes or no? So in that coordination entity, what is the metal atom? So this is the metal atom, which is a central metal atom. And this central metal atom, it bonded to the other ligands in a fixed way. Okay. And that's also in a particular geometrical arrangement. For suppose you take M, it will be like this. So there will be fixed ligands that are surrounding this metal, central metal atom. Okay. So definite geometrical arrangement around it. You understood? So what is metal atom? Any doubts? So remember, this is the central metal atom. Okay. So next one. So see here. In a coordination entity, the atom or ion to which fixed number of ions or groups bound in a definite geometrical arrangement that we know as central atom or ion. Okay. And remember, here the central atom or ion, it's always a Lewis acid. Okay. So Lewis acid, we say it as it is accepting the lone pair. Accept lone pair. Or you can say lone pair acceptors. Okay. Next one. So let's write the formula MlN A plus X A minus. So tell me, what is L here? What is L here? What is L here?
Ligand.
Huh?
Ligand, sir.
Ligand. Okay. So L is called the ligand here. So how do you differentiate? How do you tell this ligand? So it's an electron-rich species bound to the central atom or ion inside the square brackets are known as the ligands. Okay. So remember this. So usually this ligand, it will act like a Lewis base. Okay. Whereas the central metal atom, it acts like a Lewis acid. This will counter that. So it will act like a Lewis base. So what is Lewis base? Lewis base, it's nothing but the one which donates the electrons to the central metal atom. See, he is having so much of electrons. So you want to donate the electrons. He will donate to the central atom. That's how the bond formation will happen between the Lewis acid and base. Okay. So donates the electron to central atom. So he is said to be the Lewis base. Okay. So you can take the example here. The cobalt NS3 2 plus 3. Okay. So in this example, what is the ligand is the NS3. Okay. So this is the ligand. And how many ligands are there here? 2 ligands are there. Sorry, this is actual 6. 6 ligands are there. Okay. And how many, what is the central metal atom? Here, cobalt. So this cobalt, it is having CO plus 3. Okay. And this one, it's minus 6. So we'll be seeing that overall charge calculation, all that things we'll be seeing. Is that clear? So remember here ammonium donates lone pair of electrons to the central atom. Okay. And that's how they will be forming the coordinate covalent bond with the central cobalt atom. Okay. So remember this. This is very, very important. So NH3 molecule, it acts like a ligand. So which will donate lone pair of electrons and form coordinated covalent bond. Right, what is coordinated covalent bond? With central cobalt ion. Tell me, you guys know what is coordinated covalent bond? Mandara, tell me what is coordinated covalent bond? Mandara, are you there?
Yes, sir.
What is coordinated covalent bond? Shrikar? Shrikar,
Yes, sir.
what is coordinated covalent bond?
Sir, I know what is covalent bond, but coordinated, I don't know.
Banu, what is coordinated covalent bond?
Uh,
Yes. What is coordinated covalent bond? Arey, what you studied in the chemical bonding, yaar? Okay, see guys, I'll quickly tell. So tell me, what is ionic bond? What is ionic bond? Come on, guys, tell me. What
A
is ionic
bond
bond?
formed by complete transfers of
Complete transfer of.
valence electrons, sir.
Okay, for suppose let me take a sodium, which is having 2 comma 8 comma 1. Okay, and you take a chlorine, which is having 2 comma 8 comma 7. Yes or no? So one is 2 comma 8 comma 1, the other one is 2 comma 8 comma 7. So in this, we know the outer shell, the outermost should contain the octet configuration. Here it is 8. Okay. So here its outermost electron is 8, and here the outermost electron is 7. So if you see here, one electron, it has to be given to the chlorine. So it will become 2 comma 8. The sodium will be stable. And the chlorine, it will come 2 comma 8 comma 8. So if you see here, the chlorine is Cl plus 1 and the sodium is minus 1 and the sodium is plus 1. Why? Because the sodium has donated 1 electron to the chlorine. So it got the plus 1 charge. And here the chlorine gained 1 electron. So it got minus 1 charge. So both are opposite charges. There will be electrostatic bond between them and it will form NaCl because we know opposite charges attract each other. So that's how ionic bond is formed. The same like that, but somewhat different in the covalent bond. So in the covalent bond, what happened? So one guy is having, 1 second, someone is joining. Dibanshi, Gargi, can we start the class later?
So what timing? So what time?
I'll let you know by the afternoon. So if we can take the class, or I'll let you know, or else we'll start from tomorrow. Okay?
Okay, sir.
Okay,
Yeah.
sir.
Okay, guys. Okay, see here. So covalent bond. For suppose let's take an example. I have 2 red pens. Okay. I have a wait 1 second. I have a 1 red pen. Let's say A, and the B one is having black pen. Okay. So for writing the notes, I need both red and black. So what happens? So A will give its red pen for using, B will give its black pen. But still A will use this red pen as well as black pen. B will use both red and black. So that's how a bond shared between the 2 persons. And in this, both are involving in the sharing, right? A is also donating the red pen, B is also donating the black pen. So both are involved. So that kind we called it as covalent bond. What is coordinated covalent bond is, for suppose A and B. So A is having 2 black pens and B doesn't bring anything. But still B is good friend to the A. So what you do, A will donate the black pen to the B, or you can say instead of black, let's take different color. So A will give its red pen to the B. So B will use the red pen. Also A will use the red pen. So that means here 2 persons are contributing. Sorry, only 1 person is contributing, but sharing by both. That's called the coordinated covalent bond. Understood? So in covalent bond, what's happening? Both are involving in the, uh, I mean, giving the electrons. Okay. So both are contributing in that case. But here, only one is contributing, but both are utilizing. So A is a good friend to the B. So what you do, A will share its electron to the B, but B doesn't share any electrons, but it will utilize both electrons. Understood? So that's why it is also called as the kind of dative bond. Is that clear? And what electrons you will share? The extra electrons. What is those extra electrons? Usually the bond pair of electrons will involve in the bonding. The other electrons which will not usually involve in the electrons is lone pair. So here the lone pair, the A shares with the B. Understood? If it's completely transferred, then we call it as ionic. If both are contributing, we call it as covalent. But only A is contributing and utilized by both. So we call it as coordinated covalent bonding. Is that clear? Understood or not?
Yes, sir.
Yes, sir.
Okay. So just remember this. Okay. So here what happens with ammonia is ammonia donates its lone pair of electrons to the cobalt. Okay. You will not say donate. Actually, it shares the lone pair of electrons to the cobalt. But in this, cobalt is not contributing, it is just using it. Okay. So that's what. And this name is actually hexa-amino cobalt 3 complex ion. Here we say 3 because the charge is +3. Okay. So next. One more thing. So M, L, N, A plus, X, A minus. Okay. So in this A plus, charge on the coordination entity. So this entire thing we call it as coordination entity. So charge on the coordination entity. And here, this entire thing we call it as coordination sphere. Okay. So just remember, this is the coordination entity, charge on the coordination entity, and this small thing, MLN, we call it as coordination sphere. Okay, so this with the charge, so charge on the coordination entity, and this small thing we'll call it as coordination sphere. I'll tell you what is this coordination sphere. So see, a coordination sphere means the central atom or ion and the ligands attached to it enclosed in the square bracket. You can see here. So there's a central atom and the ligands, and it is enclosed in the square bracket. That we called it as collectively the coordination sphere. Okay, along with the electrical charge on it. Remember this. So this entire thing, we call it as the coordination sphere, including the charge. Okay, but if you consider only this without the charge, it's a coordination entity. So remember, in the CO NS3 6 Cl3. So tell me, what is the coordination entity in this? Sorry, coordination sphere in this? What is the coordination sphere in this? This is important because in further explanations, we need to know what is coordination sphere. At the time, if you don't understand what is coordination sphere, it will be a problem. So
So
tell me, huh?
So the whole thing, sir.
This entire thing, see here what I said, the central atom, ligands attached to it, enclosed in the square bracket only comes under the coordination sphere. That means only this part. Why you are taking this one, Xa minus? That means Cl minus 3, it will Cl minus, it will not come in the coordination sphere. Only this part will come. Okay. So this we call it as coordination sphere. Okay. So remember CO NS3 6 minus 3 will come under the coordination sphere. Okay. So these coordination spheres, or you can say the complex spheres, they are of three types. One is, just know it, you don't need to remember, but just know it, like kind of extra information. So remember, what is coordination sphere? It represents the central metal atom or ion that is directly attached to the ligand, and it is enclosed in the square brackets. Okay, that we call it as coordination sphere. This coordination sphere can be three types. One is cationic complexes, or anionic complexes, or neutral complexes. Okay, so these are the three: cationic complexes, anionic complexes, neutral complexes. So what is this cationic complexes? Okay, so actually cationic, that means it will carry the coordination sphere, whatever this sphere is there, it's consisting the positive charge. For suppose if I break this, it will be containing the +3 charge, right? So this comes under the cationic complexes, which contains positive charge. Okay, you can take ZnNS3 4 + 2 as well, example. So remember Zn NS3 4 + 2. So this is a cationic complex. If you take the anionic complex, FeCN 6 4 minus. So from this you can say, what is the anionic complexes? Something that consists of negative charge. If it not contains positive charge, if it not contains negative charge, then we call it as the neural complexes. Sorry, the neutral complexes. You can take the example NiCO4. Okay, that means you can say here, whatever the nickel charge is there, it completely balanced with the cobalt, and there is no net resultant charge. Whereas here there is some extra charge is there. That's why it's a actually it's a -4. Okay, whereas here there's a +2 charge is there. That means the net charge, it is not balanced and it is maintaining +2. That has to be balanced by some extra metal outside. Sorry, the extra electronegative atom outside. So like chlorine, all those. Is that clear? What is meaning of coordination sphere? Any doubts?
Yes, sir.
Yes, sir.
Okay. So see here, what is the difference between the coordination entity and coordination sphere? Coordination entity, it's a collection of the central atom, ligand, and surrounding the atom. Ligand surrounding the atom. Okay. Whereas the coordination sphere, coordination entity given with electric charge. That means you don't include the charge here. It is a coordination entity. You also include this charge present here. That's a +3. You include this charge, then we call it as the coordination sphere. Remember this. This is the coordination sphere. Okay. And if you take only this part, don't include the +3 charge, then it is a coordination entity. Understood? Is that clear?
Yes, sir.
Yeah. And coordination entity, it can be the central atom or it may not be. Okay. I mean, it can be the metal atom or it may not be. For suppose you take BF4 minus. Okay. So here It's not a metal atom, but still it's a coordination entity. Okay, and you take NiCO2 full charge, please, with the minus, then it will comes under coordination sphere. So remember, just notice the difference between coordination entity and coordination sphere. And then we have some counter ions, that is M, L, N. See, I'm explaining these things many times because there will be huge number of questions on this. They will be asking you coordination sphere, coordination entity. You should not confuse with the words. So that's why I'm putting more pressure. So this is the counter ion. Okay. So this will be always opposite charge to this ion. Okay. So I mean always opposite to the coordination sphere. Opposite to coordination sphere. Okay. So charge will be opposite to coordination sphere charge. You can take examples here like cobalt NS3 6 plus 3 3Cl minus. So here this 3Cl minus is the counter ion. Okay. So see here, counter ion, when there are two coordination spheres joined together by ionization sphere. Okay. So that we call it as the counter ion as complex compound. Okay. So remember, counter ion as complex compound means you have when there are two coordination spheres are there, they join together by ionization sphere. First, suppose, let me give you an example. Ag NS3 twice. Okay. So this is comes under something like this one. Okay. So if you see here, I can break down this. Okay. I can break down here. If I break down, this will be positive charge and this will be negative charge. That's one thing. Okay. So see here, when there are two coordination spheres are there, this is one coordination sphere and this is coordination sphere. They both are joined by ionization sphere. Okay. That means this is an ion, this is an ion, both are opposite ions, so they join together. Understood? You can take a other example also, like CrNS3 6 plus 3. So this is one coordination sphere which is joined with another coordination sphere, COCN6 minus 3. So both are opposite charges, they attract towards each other and they joined. Is that clear? So see, ionization sphere. What is ionization sphere? The molecule or ionic space is present outside the coordination sphere. That means whatever that counterpart is there, that actually comes under the ionization sphere. First, suppose you take an example. FeCN6 4 minus. Okay. So here, what comes under the ionization sphere? Let me write. So this comes under the coordination sphere. We know that. And this will be balanced by 4K plus. Okay. There will be K4 here. So here, whatever this 4K plus is there, this will come under the ionization sphere. Okay. And whatever this thing is there, This comes under the coordination sphere. Is that clear? So what is meaning of ionization sphere and the coordination sphere? So here the ionization sphere is K plus, whereas the coordination sphere is FeCN6 4 minus. Any doubts? And coordination number. In order to know the coordination number, just know what is this ligand number. Okay, so ligand number, let me write. We know the formula ML N A plus X A minus. Okay, here whatever the N is there here, this N, this we call it as the ligand number, or how many ligands are there, number of ligands. Okay, and coming to the coordination number, you can define this as the coordination number, that is Cn, of a metal ion in a complex can be defined as number of okay. So see here, what is coordination number? Okay, that's a metal coordination number of a metal ion in a complex. That means metal ion in the sense the central atom. Okay, it is number of ligands that are directly bonded to the central atom. Okay, so you can see here, like for suppose CO and S3 6 3 plus 3Cl minus. Okay, so this is the coordination number. You may have questions, sir, then what is ligand number and difference between the coordination number? See, sometimes it can contain two or three ligands. It no need to be NS3. It could be something else, CO2. This is 3. At that time, you can't say the coordination number is only 3. There's also 3 plus 2. Okay, so just remember this. So you can say the coordination number means the number of ligands that are directly attached to the cobalt. Okay, or the central metal atom. So that's called coordination number. So you understood what is the difference between the coordination number and the ligand number?
So could you repeat?
See, coordination number means, for suppose you take this cobalt is NS3, here NS3, here NS3, here NS3. So this is the -3. This is the coordination number, and this is balanced by 3Cl minus ions. So this we call it as coordination sphere. In that, whatever the ammonias, the ligands are there, those are directly attached to the cobalt. We call it as the coordination number. For suppose 1, 2, 3, 4, 5, 6. Okay. Sometimes I can write like this cobalt like NS3. I'm taking just random example here. It no need to be like that. So let's say CO2, there are 3. Okay, instead of NS3, there are CO2 are also attached. Now, if you ask the coordination number of this entire compound is 2 plus 3, 5, right? If I just ask the ligand number for ammonia, it's 2. For ligand number for carbon dioxide is 3. You understood? What is the difference between the coordination number and the ligand number?
Yes, sir.
Yeah. So tell me this. So PT Cl 6 2 minus. So tell me, what is the coordination number for PT? Coordination number for PT. What is it? Come on, guys, tell me. What is the coordination number for PT here? Banu? Banu? She is not there. Mandara, you tell me what is the answer for this? Mandara, are you there? Come.
Yes, sir.
Then respond, no? So tell me what is the answer?
6, sir.
Yes. So see here, 6 chlorines were attached to PT. So the coordination number is 6. Shrikar, you tell me this. What is the coordination number for this? Tell me what is the coordination number for this?
4, sir.
Yeah, it is 4. Okay. So next one, coordination polyhedron. It's nothing but the spatial arrangement of ligands. Atoms that are directly attached to the central atom defines a coordination polyhedron. Okay, that means there are different polyhedrons are there. I'll show you. If I show you image, you will understand. So they are different. One is octahedral. One is square planar. These are the common ones, which mostly seen. And there is tetrahedral. Okay. So see here, what is this? The spatial arrangement of the ligand atoms. That means whatever the central atom is there, this is arranged, surrounded by the ligands, right? So how these ligands are directly attached to the central atom and how they are spatially arranged. So that's called the polyhedron. Okay. So you can see here there are different types. One is octahedral, square planar, the tetrahedral. You can see the structures here. So octahedral, tetrahedral, square planar. Here you can see this is the central atom and here it is surrounded by the ligands. So all the spatial arrangement of these ligands, we will be giving the names. One is octahedral, tetrahedral, and square planar. Next one, oxidation number of the central metal atom. This is very, very important thing. Okay. So many previous year questions came on this. So the charge that a metal would carry if all the ligands are removed with the electron pairs that are shared with the central atom, we call it as oxidation number. Simply that means whatever the charge present on the central atom, that's nothing but this one, oxidation number. Okay. For suppose, how do we calculate that? Let's take a example, copper CN4 3 minus. So in this, what is the oxidation number of the central metal atom? Let's take, this is the X. We don't know. So let's take X. And we know the charge of the cyanide ion is always -1, right? Cn -1. So I'll be taking the charge on this is -1. And the overall net charge is -3. So I'll be taking like this. The formula is this should be equal to this. That means whatever the charge that is present on the copper, which is multiplied with 4 minus 1. You understood why I'm multiplying here? That means I should add all these things. Okay. So here Cn, I know it's a -1 and there are such 4 Cns are there. So 4 into -1. This should be equal to -3 because the overall charge is -3. So I'll be getting the answer. So it will be -4 going on the other side, it will become +4. So -3 plus 4, it is +1 charge. So the oxidation charge, or you can say Okay, the oxidation number of copper is +1. Understood? Oxidation number of copper is equals to +1. Is that clear?
Yes, sir.
Yes,
Mandara,
sir.
what about you? Yeah.
Yes, sir.
Okay, guys, then we'll stop here. Any doubts?
No, sir.
Okay, okay then. Bye bye. Take care.
Thank you, sir.
Thank you, sir.
Thank you.